Tonight, we're going to confront one of the most unsettling questions in all of science. There are roughly 200 billion trillion stars in the observable universe. Many of them are billions of years older than our sun. Most of them have planets. The chemistry of life is everywhere. The ingredients are common. The time has been more than sufficient. By every reasonable calculation, the universe should be absolutely teeming with life. Not just microbial life, but civilizations. Thousands of them, maybe millions. And yet, when we point our telescopes at the sky, when we listen for signals, when we search for any trace of intelligence beyond Earth, we find nothing. Absolute silence. The universe appears completely empty. And the deeper you look into why that silence exists, the more disturbing the possible answers become. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with the numbers. Because the numbers are where this whole mystery begins, and the numbers are staggering. The observable universe, the part of the cosmos from which light has had time to reach us since the Big Bang, is about 93 billion light years across. Within that volume, astronomers estimate there are roughly 2 trillion galaxies. Not million, not billion. 2 trillion separate galaxies, each one a vast collection of stars bound together by gravity, drifting through the expanding darkness of space. Some of these galaxies are small, containing only a few million stars. Others are enormous, home to trillions of stars packed into spirals and elliptical structures that stretch across hundreds of thousands of light years. Our own galaxy, the Milky Way, contains somewhere between 100 billion and 400 billion stars. The exact number is difficult to pin down because we're inside the galaxy, and dust and distance obscure our view of much of it. But even a conservative estimate puts the number around 200 billion stars in our galaxy alone. Now, multiply that by 2 trillion galaxies. The total number of stars in the observable universe comes out to something in the range of 200 billion trillion. That's a 2 followed by 23 zeros. It's a number so large that it's almost meaningless to the human brain. We didn't evolve to comprehend quantities this vast. We evolved to count the members of our tribe, the animals in a herd, the days until the seasons changed. 200 billion trillion is so far beyond our cognitive capacity that it might as well be infinity. But it's not infinity. It's a real, finite number. To put it in some kind of perspective, there are more stars in the observable universe than there are grains of sand on every beach on Earth. Every beach, every coastline, every desert, every sandbox, add them all together and you still don't have as many grains of sand as there are stars in the cosmos. That comparison has been checked by scientists who actually estimated both numbers, and the stars win. The universe contains more suns than Earth contains grains of sand, and each one of those stars is a sun. A nuclear furnace converting hydrogen into helium, pouring light and energy into the surrounding space. Many of them are similar to our own sun, a yellow dwarf star of average size and brightness. The kind of star that has proven perfectly capable of supporting a planet with life. And here's what makes this number truly significant. We now know that most of these stars have planets. This isn't speculation. This isn't science fiction. This is observed fact, confirmed by decades of careful astronomical observation. Before the 1990s, we had no direct evidence that any star other than our sun had planets orbiting it. We suspected they did, but we couldn't prove it. Our solar system might have been unique for all we knew. Then, in 1992, astronomers detected the first planets orbiting another star, a pulsar called PSRB 1257 plus 12. In 1995, the first exoplanet orbiting a Sun-like star was confirmed. A gas giant called 51 Pegasi b orbiting a star about 50 light-years from Earth. And since then, the discoveries have come in a flood. The Kepler Space Telescope, launched by NASA in 2009, was specifically designed to find exoplanets. It stared at a single patch of sky for years, monitoring over 150,000 stars simultaneously, watching for the tiny dip in brightness that occurs when a planet passes in front of its host star. This technique is called the transit method, and it works because when a planet crosses between us and its star, it blocks a tiny fraction of the star's light. The dimming is subtle, sometimes less than 1%, but Kepler was sensitive enough to detect it. And what Kepler found changed everything. Over the course of its mission, Kepler confirmed the existence of over 2,700 exoplanets and identified thousands more candidates. But the real breakthrough wasn't just the number of planets it found, it was what those numbers implied about the broader galaxy. By analyzing how many stars in its field of view had detectable planets, and accounting for the fact that the transit method only works when a planet's orbit happens to be aligned with our line of sight, astronomers were able to estimate how common planets really are. The answer is that planets are everywhere. Statistical analyses of Kepler data suggest that on average, every star in the Milky Way has at least one planet. Some have 2, 3, 5, 8, or more. The galaxy isn't just dotted with occasional planetary systems, it's saturated with them. There are likely more planets in the Milky Way than there are stars. Current estimates suggest somewhere between 100 billion and several hundred billion planets in our galaxy alone. And many of those planets are rocky worlds similar in size to Earth. Not gas giants like Jupiter or Saturn, but solid worlds with surfaces you could stand on. Worlds where liquid water could pool and flow. This was a revelation. Before Kepler, some scientists worried that planets might be rare, that our solar system might be unusual, a cosmic accident that produced an unlikely family of worlds. Kepler demolished that concern. Planets are the norm, not the exception. Stars without planets are the oddity, the outliers. The default state of a star, it turns out, is to have a family of worlds orbiting it. The universe is filled with planets. More worlds than we could ever count. More worlds than we could ever visit, even given unlimited time and unlimited technology. And every year, as our telescopes improve, we find more of them. As of 2024, we've confirmed the existence of over 5,700 exoplanets, with thousands more candidates waiting to be verified. And those are just the ones we've managed to detect. The true number is vastly higher, but having planets isn't enough. For our question, for the mystery we're trying to understand tonight, what matters is whether any of those planets could support life. And this is where the story gets even more compelling, because a surprising number of those planets orbit in what astronomers call the habitable zone. The habitable zone is the region around a star where temperatures are right for liquid water to exist on a planet's surface. Not too close to the star where water would boil away. Not too far where it would freeze solid. But in that narrow band where water can remain liquid, flowing across the surface, filling oceans and rivers and lakes. Liquid water is considered essential for life as we know it. Every living thing on Earth depends on water. Every biochemical reaction that sustains life occurs in water. Wherever we find liquid water on Earth, we find life, even in the most extreme environments. Boiling hot springs, freezing Antarctic lakes, lightless caves deep underground, acidic mine drainage, the crushing pressures of the deep ocean floor. If there's liquid water, there's life, without exception. So how many planets sit in this habitable zone? Based on Kepler data and subsequent observations from missions like the Transiting Exoplanet Survey Satellite, or TESS, astronomers estimate that roughly 20 to 25% of Sun-like stars have at least one rocky planet in their habitable zone. That's about 1 in 4 or 1 in 5. Apply that fraction to the Milky Way's hundreds of billions of stars, and you get tens of billions of potentially habitable rocky worlds in our galaxy alone. Tens of billions, not thousands, not millions. Tens of billions of planets where conditions might be right for liquid water and potentially for life. To grasp this, imagine that every single person alive on Earth today was given their own potentially habitable planet. You'd still have planets left over, roughly 4 or 5 times over. That's how many worlds in our galaxy alone might have the right conditions for liquid water on the surfaces. And that's just counting planets around sun-like stars. Red dwarf stars, which are much smaller and cooler than the sun, are the most common type of star in the galaxy, making up about 70% of all stars. Many red dwarfs also have rocky planets in their habitable zones. The TRAPPIST-1 system, about 40 light-years from Earth, contains 7 Earth-sized planets orbiting a small red dwarf, and 3 of those planets sit in the habitable zone. All 7 planets are packed tightly together, orbiting closer to their star than Mercury orbits our Sun. But because the star is so much smaller and cooler than the Sun, those close-in orbits produce temperatures that could allow liquid water. If red dwarf systems like this are common, and early indications suggest they might be, then the total number of potentially habitable worlds in the Milky Way could be dramatically higher than estimates based on sun-like stars alone. Some estimates push it above 40 billion. 40 billion potentially habitable worlds in one galaxy. And remember, there are 2 trillion galaxies in the observable universe. The number of potentially habitable planets across the entire cosmos is so large that writing it down requires scientific notation. We're talking about truly staggering numbers in the billions of trillions. The universe is not short on real estate for life, but planets and liquid water are just the beginning. For life to arise, you also need the right chemistry. You need the building blocks, the raw materials from which living systems can assemble themselves. And here's what's remarkable. Those building blocks are everywhere. The universe is absolutely saturated with the ingredients for life. The most essential element for life as we know it is carbon. Carbon is special because of its ability to form complex molecules. It can bond with up to 4 other atoms simultaneously, creating chains, rings, and 3-dimensional structures of almost unlimited complexity. This versatility makes carbon the backbone of all known biology. Every protein, every strand of DNA, every cell membrane, every enzyme, all of it is built on a framework of carbon atoms. And carbon is one of the most abundant elements in the universe. It's produced inside stars through nuclear fusion. When massive stars die in supernova explosions, they scatter carbon and other heavy elements across space. These elements mix into clouds of gas and dust, which eventually collapse to form new stars and planets. Every carbon atom in your body was forged inside a star that died before our sun was born. But it's not just carbon. The other elements essential for life, hydrogen, oxygen, nitrogen, phosphorus, and sulfur, are also abundant throughout the cosmos. Hydrogen is the most common element in the universe by far. Oxygen is the third most common. These elements combine naturally in interstellar space to form simple organic molecules, the precursors to the complex chemistry of life. And we found these molecules everywhere we've looked. Astronomers have detected over 200 different organic molecules in interstellar space using radio telescopes. These include compounds like methanol, formaldehyde, and hydrogen cyanide, the kinds of simple molecules that serve as stepping stones toward the more complex chemistry of life. And the evidence gets stronger the closer we look. In 2006, NASA's Stardust mission returned samples from Comet Wild 2. Analysis of those samples, published in 2009, revealed glycine, the simplest amino acid, embedded in the comet's dust. Meteorites that have fallen to Earth have been found to contain amino acids, sugars, and nucleobases, the components of DNA and RNA. The Murchison meteorite, which landed in Australia in 1969, contained over 90 different amino acids, most of which are not found in terrestrial biology. These molecules weren't produced by life, they were produced by chemistry, by the natural interactions of atoms and molecules in space, on asteroids, and in the swirling disks of material around young stars. Even ethyl alcohol, ordinary drinking alcohol, has been found in massive clouds in interstellar space. One such cloud near the center of the Milky Way contains enough ethyl alcohol to fill 400 trillion pints. The chemistry of life isn't something that requires special conditions or unlikely events. It happens naturally, spontaneously, throughout the universe. The ingredients for life are not rare. They're common. They're everywhere. They're falling out of the sky. They're drifting between the stars. They're embedded in the comets and asteroids that bombard young planets. The raw materials for biology are as common in the cosmos as hydrogen and starlight. Now let's add another ingredient to this calculation: time. Because time might be the most important factor of all, and the universe has had an almost inconceivable amount of it. The universe is approximately 13.8 billion years old. The first stars formed within a few 100 million years of the Big Bang. The first galaxies assembled within the first billion years. And the heavy elements necessary for rocky planets and complex chemistry were being produced and scattered across space within the first 1 to 2 billion years. Our sun formed about 4.6 billion years ago from a cloud of gas and dust that had been enriched by generations of earlier stars. Earth formed shortly after, coalescing from the debris orbiting the young sun. And here's the critical point. Life on Earth appeared remarkably quickly once conditions became suitable. The oldest confirmed evidence of life on Earth dates to about 3.5 billion years ago, in the form of fossilized microbial mats called stromatolites, found in ancient rocks in Western Australia. But there are chemical signatures in even older rocks, dating back 3.8 billion years or more, that suggest life may have been present even earlier. Earth is about 4.5 billion years old. For the first several 100 million years, it was a hellish place. The surface was molten, glowing red and orange with rivers of liquid rock. Giant impacts were common, some so violent they could vaporize entire oceans. The entire planet was being reshaped by collisions with leftover debris from the solar system's formation. This period is called the Late Heavy Bombardment, and it lasted until about 3.9 billion years ago. During this time, Earth was essentially sterilized repeatedly. Any life that tried to gain a foothold would have been destroyed by the next major impact. The planet needed to calm down before life could take hold. Once the bombardment eased and Earth's surface cooled enough for liquid water to persist, life appeared within a few 100 million years, possibly much less. Some researchers have argued that life might have appeared almost as soon as conditions permitted, within tens of millions of years of the surface becoming habitable. A few 100 million years might sound like a long time, but in geological and cosmic terms, it's remarkably fast. Consider that complex multicellular life took another 3 billion years to evolve after those first microbes appeared. The origin of life itself seems to have been the easy part. It was the subsequent steps, the evolution of complexity, that took far longer. This suggests that life isn't something that requires an extraordinary sequence of unlikely events. If conditions are right, life seems to emerge relatively quickly, as if the chemistry of life is eager to happen, as if the transition from non-living chemistry to living systems is a natural, perhaps even inevitable step. The universe may be wired for life at the most fundamental level. This has profound implications. If life arose quickly on Earth, and if the ingredients and conditions for life are common throughout the universe, then life should be common too. There's no obvious reason why Earth should be special in this regard. The same chemistry that produced life here operates everywhere in the cosmos. The same elements, the same molecules, the same physical laws. If life is a natural consequence of the right conditions, and if those conditions exist on billions of worlds, then life should have arisen billions of times. But it gets even more compelling when you consider the age of other star systems. Our Sun is about 4.6 billion years old. It's a middle-aged star, but many stars in the Milky Way are much older. Some are 10 billion years old, more than twice the age of our Sun. These stars formed when the universe was young, and if they had planets in their habitable zones, life could have arisen on those planets billions of years before Earth even existed. Think about what that means. If a civilization arose on a planet orbiting one of these older stars, it could have had a 5 or 6 billion year head start on us. 5 or 6 billion years. To put that in perspective, life on Earth went from single-celled organisms to human civilization in about 3.5 billion years. Modern humans have existed for only about 300,000 years. Technological civilization, the kind that builds radio telescopes and sends spacecraft into orbit, has existed for barely a century. 100 years ago, we didn't have television. 200 years ago, we didn't have electricity in our homes. 300 years ago, we didn't know what the stars were made of. 1,000 years ago, we thought the Earth was at the center of the universe. 10,000 years ago, we hadn't invented writing. And yet in that tiny sliver of time, we went from stone tools to spacecraft. Now imagine a civilization that had not thousands of years, but billions of years to develop. In 5 or 6 billion years, a civilization could have advanced to levels we can't even imagine. They could have developed technologies that seem like magic to us. They could have spread across their entire galaxy, colonizing world after world. They could have built structures visible across interstellar distances. They could have reshaped their corner of the universe in ways that would be obvious to anyone looking. Even with technologies not much more advanced than what we currently possess, a civilization could theoretically colonize an entire galaxy in a relatively short time by cosmic standards. If a civilization developed interstellar travel, even at a small fraction of the speed of light, and began sending colony ships to nearby stars, and those colonies in turn sent out their own colony ships, the entire Milky Way could be settled in somewhere between 10 million and 100 million years. That sounds like a long time, but the galaxy is over 13 billion years old. There has been more than enough time for this to have happened, not once, but many times over. Even if you don't assume faster than light travel, even if you assume civilizations can only travel at 1 or 2% the speed of light, the galaxy could still be fully colonized in 50 to 100 million years. That's less than 1% of the galaxy's age. The math is simple and unforgiving. If even one civilization in the entire history of the Milky Way developed the ability and desire to spread, they could have reached every corner of the galaxy by now with time to spare, hundreds of times over. The galaxy has existed for over 13 billion years. It only takes one civilization at any point during those 13 billion years to start expanding. And once the expansion begins, it fills the galaxy in a cosmically insignificant amount of time. And it's not just colonization. A sufficiently advanced civilization would leave traces that we could detect even without direct contact. They might build enormous structures to capture energy from their star. In 1960, physicist Freeman Dyson proposed that an advanced civilization might construct a shell or swarm of structures around its star to capture most or all of the star's energy output. These hypothetical structures, now called Dyson spheres or Dyson swarms, would be detectable because they would alter the star's light signature. The star would appear dimmer in visible light, but brighter in infrared, because the structures would absorb visible light and re-radiate it as heat. Astronomers have actually searched for these signatures, scanning thousands of stars looking for unexplained infrared excesses. They might alter the chemistry of planetary atmospheres through industrial activity. They might produce electromagnetic radiation, radio waves, microwaves, laser pulses as a byproduct of their technology, just as Earth leaks radio and television signals into space. Even if they weren't trying to communicate with us, even if they had no interest in making contact, the sheer scale of a galaxy-spanning civilization should produce detectable signatures. We should see something. An unusual infrared glow from a star system partially enclosed in energy-collecting structures. A pattern in radio emissions that couldn't be produced by natural processes. An unexplained change in a star's brightness. Chemical signatures in a planet's atmosphere that could only be produced by industry. Something. Anything. So let's put it all together. The universe contains roughly 200 billion trillion stars. Most of them have planets. Tens of billions of those planets in our galaxy alone sit in habitable zones where liquid water could exist. The chemical building blocks of life are found everywhere, in interstellar clouds, on comets, embedded in meteorites, scattered across the cosmos by dying stars. Life on Earth appeared quickly once conditions allowed it, suggesting that the origin of life is not extraordinarily improbable. Many star systems are billions of years older than ours, providing ample time for life to arise and evolve, far beyond anything we've achieved. And even conservative estimates of how quickly a technological civilization could spread suggests that the galaxy should have been colonized many times over by now. Every piece of evidence, every calculation, every observation points in the same direction. The universe should be full of life. Not just microbial life hiding in subsurface oceans on distant moons, but intelligent, technological civilizations that have had billions of years to develop, expand, and reshape their environments on cosmic scales. The ingredients are there, the time is there, the opportunities are there. By any reasonable reckoning, we should not be alone. The astronomer Carl Sagan once estimated that there could be as many as 1 million technological civilizations in the Milky Way alone. Other scientists have offered estimates ranging from a few thousand to several million. Even the most pessimistic calculations, those that assign extremely low probabilities to each step in the emergence of intelligent life, still tend to produce numbers greater than 1. The math keeps insisting that someone else should be out there. And this isn't just idle speculation. This is the conclusion that falls naturally out of what we know about the universe. The number of stars, the abundance of planets, the universality of chemistry, the age of the cosmos, all of it builds a case that is, on paper, overwhelming. Life should be common. Intelligence should have arisen many times. Civilization should have had time to spread across galaxies. The universe should be buzzing with activity, filled with signals and structures and evidence of minds at work. This expectation isn't based on optimism or wishful thinking. It's based on observations, real data gathered by real telescopes and spacecraft over decades of careful scientific work. The Kepler mission showed us that planets are everywhere. Spectroscopic analysis showed us that the elements of life are everywhere. The geological record on Earth showed us that life arises quickly when conditions permit. The age of the universe tells us that time is not a limiting factor. Studies of extremophiles on Earth, organisms that thrive in conditions we once thought impossible for life, showed us that life is far more resilient and adaptable than we imagined. Every line of evidence converges on the same conclusion. The universe should be teeming with life. Not might be, should be. The numbers demand it. The chemistry supports it. The timescales allow it. The physics permits it. Everything we know about the universe tells us that life should be common, that intelligence should have arisen many times, that civilization should have had ample opportunity to develop and spread across entire galaxies. And that's what makes what comes next so deeply, profoundly unsettling. Because when we actually look out at the cosmos, when we listen with our most sensitive instruments, when we search for any sign at all that someone else is out there, we find nothing. The universe is silent. The sky is empty. There are no signals, no structures, no evidence of any kind that any other intelligence has ever existed anywhere in the observable universe. Every frequency we've monitored, every star system we've examined, every corner of the sky we've surveyed, nothing. Just the natural hum of pulsars and the background glow of the Big Bang. But no voices, no messages, no signs that anyone is home. The expectation says the universe should be full. The observation says it appears to be empty. And the gap between those two facts, the chasm between what the numbers predict and what we actually see, is one of the deepest and most disturbing mysteries in all of science. That gap has a name. And understanding it requires us to confront possibilities that are as fascinating as they are unsettling. It was the summer of 1950. A group of physicists were walking to lunch at the Los Alamos National Laboratory in New Mexico, the same facility where the atomic bomb had been designed just a few years earlier. Among them was Enrico Fermi, one of the most brilliant physicists of the 20th century. Fermi had played a central role in building the first nuclear reactor. He had won the Nobel Prize in Physics in 1938. He was known for his extraordinary ability to make quick, accurate calculations about seemingly impossible questions. His colleagues called these Fermi estimates, and they became famous in physics. Give Fermi a seemingly unanswerable question. How many piano tuners are there in Chicago? How much energy does the sun produce? How far can a nuclear blast be felt? And he could arrive at a reasonable answer in minutes using nothing but logic and rough numbers. That day, the conversation at lunch had turned to a recent wave of reported flying saucer sightings that had swept across the United States. The late 1940s and early 1950s were a golden age of UFO reports. People across the country were claiming to see strange objects in the sky. Newspapers ran breathless headlines. The Air Force launched investigations. The public was fascinated, and even serious scientists found the topic hard to ignore completely. A New Yorker magazine cartoon had recently depicted aliens stealing public trash cans from the streets of New York City, offering a humorous explanation for a rash of missing garbage cans, and someone at the table brought it up. There was laughter. The physicists were having fun with the idea of extraterrestrial visitors. The mood was light, playful. No one was taking it seriously. Then the conversation moved on to other things. They sat down to eat, and in the middle of lunch, seemingly out of nowhere, after the group had been talking about something else entirely, Fermi suddenly looked up and asked a question that has haunted science ever since. Where's everybody? His colleagues immediately understood what he meant. He wasn't asking about the other people in the cafeteria. He was asking about extraterrestrial civilizations. Given the vast number of stars, given the age of the universe, given the likelihood that other civilizations should have arisen and had time to spread across the galaxy, where were they? Why hadn't they shown up? Why hadn't we detected any evidence of their existence? The question hung in the air. No one had a satisfying answer, and more than 75 years later, no one has a satisfying answer still. This is the Fermi Paradox. It's not just a casual question posed over sandwiches. It's a formal, scientific problem. One of the most important open questions in astronomy, astrobiology, and physics. The paradox can be stated simply. The universe is vast and old. The conditions for life appear to be common. The time available for civilizations to arise and spread is enormous. Therefore, we should expect to see evidence of other civilizations. But we don't. The expected observation and the actual observation directly contradict each other. That contradiction is the paradox. What makes the Fermi Paradox so powerful is that it's not based on speculation. It's based on things we actually know. We know the universe contains an enormous number of stars. We know most stars have planets. We know the building blocks of life are common. We know life arose quickly on Earth, once conditions allowed it. We know the universe is old enough for civilizations to have arisen billions of years ago. These are established facts, backed by decades of observation and measurement. The paradox arises not from wild guesses, but from the straightforward application of known science. And the silence we observe is not a matter of opinion. It's a matter of fact. We have looked carefully and systematically, and we have found nothing. Before we get into what we've actually searched for and what we haven't found, It's worth talking about a framework that scientists use to think about this problem. In 1961, astronomer Frank Drake convened a meeting at the National Radio Astronomy Observatory in Greenbank, West Virginia. The purpose was to discuss the scientific search for extraterrestrial intelligence. To organize the discussion, Drake wrote an equation on the blackboard. It was never meant to be a precise calculation. It was a way of breaking down the question of how many detectable civilizations might exist in our galaxy into a series of smaller, more manageable questions. That equation became known as the Drake equation, and it's been at the center of discussions about extraterrestrial life ever since. The Drake equation multiplies together a series of factors: the rate at which new stars form in the galaxy, the fraction of those stars that have planets, the number of planets per star that could potentially support life, the fraction of those planets where life actually arises, the fraction of life-bearing planets where intelligent life evolves, the fraction of intelligent civilizations that develop technology capable of sending detectable signals into space, and finally, the length of time such civilizations survive and remain detectable. Multiply all these factors together, and you get an estimate of the number of communicating civilizations in the Milky Way at any given time. The beauty of the equation is that it takes an overwhelming question, are we alone in the galaxy, and breaks it into 7 smaller questions that can each be discussed individually. Some of those smaller questions have reasonably well-known answers, others are completely unknown. And the value of the equation isn't that it gives us a number we can trust, it's that it shows us precisely where our ignorance begins. Now, the Drake equation has been both praised and criticized over the decades. Its strength is that it breaks a seemingly impossible question into pieces that can each be discussed and estimated separately. Its weakness is that we don't actually know the values of most of those factors. We have decent estimates for some of them. We know the rate of star formation in the Milky Way is roughly 1 to 3 new stars per year. We know that most stars have planets. We have reasonable guesses about how many planets sit in habitable zones. But after that, the uncertainties grow enormous. We don't know how often life arises on a habitable planet. We don't know how often life evolves intelligence. We don't know how often intelligent life develops technology. And we certainly don't know how long technological civilizations typically survive. Depending on what values you plug into the Drake equation, you can get answers ranging from many millions of civilizations in the galaxy to less than 1. The equation doesn't give us a definitive answer. It gives us a framework for thinking about the problem. It shows us where our ignorance lies and where we need more data. And the critical insight of the Drake equation is this: even if you assign very pessimistic values to every factor, even if you assume that life is rare, intelligence is rarer, and technology is rarest of all, the sheer number of stars in the galaxy, hundreds of billions, tends to produce an answer greater than 0. The numbers keep insisting that we shouldn't be alone, and yet the observational evidence keeps insisting that we appear to be. So what have we actually done to search? How thoroughly have we looked for signs of other civilizations? The answer might surprise you. We've been searching for over 60 years, using increasingly sophisticated technology, and the scope of that search is both impressive and, in cosmic terms, humblingly small. The modern search for extraterrestrial intelligence began in 1960 when astronomer Frank Drake, the same Frank Drake who created the equation, pointed a 26-meter radio telescope at two nearby sun-like stars, Tau Ceti and Epsilon Eridani. Both stars are within about 12 light-years of Earth, close enough that even a relatively weak signal might be detectable. The project was called Ozma, named after the princess of the fictional land of Oz, a distant and unreachable place filled with strange beings. It was a bold and somewhat audacious project for its time. Many scientists considered the search for alien signals to be fringe science, barely respectable, more science fiction than serious research. Drake listened for artificial radio signals, patterns that couldn't be produced by natural processes. He listened for a total of about 150 hours across several months. He heard nothing but the natural noise of the cosmos. But the project established something important. It showed that the search for extraterrestrial intelligence could be conducted as rigorous science, using real instruments and real methodology, not speculation and wishful thinking. Since then, the search has expanded enormously. The most famous effort is SETI, the search for extraterrestrial intelligence. SETI encompasses dozens of projects spanning decades, involving some of the most powerful radio telescopes ever built. The basic idea behind most SETI searches is straightforward. Radio waves travel at the speed of light. They can cross interstellar distances. A technological civilization might deliberately broadcast signals into space, trying to announce its presence, or it might simply leak radio emissions as a byproduct of its technology, just as Earth has been leaking television broadcasts, radar signals, and radio transmissions into space for the past century. Either way, those signals could potentially be detected by sensitive radio telescopes on Earth. Over the decades, SETI projects have surveyed thousands of stars, scanning across millions of radio frequencies, listening for anything that looks artificial. The mega-channel extraterrestrial assay, known as Project Meta, scanned over 8 million radio channels simultaneously. Project Phoenix, which ran from 1995 to 2004, targeted about 800 nearby sun-like stars using some of the largest radio telescopes in the world. The Allen Telescope Array in Northern California was designed specifically for SETI, capable of scanning multiple targets simultaneously across a wide range of frequencies. More recently, the Breakthrough Listen initiative, funded in 2015 by investor Yuri Milner, became the most comprehensive SETI program ever launched. Breakthrough Listen uses some of the world's largest and most sensitive radio telescopes, including the Green Bank Telescope in West Virginia and the Parkes Telescope in Australia. It surveys the 1 million stars closest to Earth, the 100 closest galaxies, and the entire galactic plane. It scans billions of radio channels and processes enormous amounts of data using advanced algorithms designed to detect artificial signals hidden in the noise. And the result of all this searching? Nothing. No confirmed signal from an extraterrestrial civilization. Not once, in over 60 years of listening. Billions of data points analyzed. Millions of stars surveyed. Thousands of hours of telescope time devoted to the search. And the answer has been the same every single time. Silence. Static. The natural hum of pulsars, quasars, and the cosmic microwave background. But no voices, no messages, no artificial patterns. There have been a few tantalizing moments, brief flickers that made scientists hold their breath before the excitement faded. In 1977, a radio telescope at Ohio State University detected a strong narrowband signal that lasted 72 seconds. It was so remarkable that the astronomer on duty, Jerry Eman, circled the signal on the computer printout and wrote the word "wow" next to it. The wow signal, as it became known, has never been satisfactorily explained. It had many characteristics you'd expect from an artificial extraterrestrial signal. It was at a frequency near the hydrogen line, a frequency that scientists had long speculated would be a logical choice for interstellar communication, because hydrogen is the most common element in the universe, and any advanced civilization would know its frequency. But the signal was never detected again. Despite numerous attempts to re-observe it, pointing telescopes at the same patch of sky, listening on the same frequency, the signal never repeated. A one-time signal that can't be verified isn't evidence of anything. It's a curiosity, an unsolved mystery, but not proof of extraterrestrial intelligence. Beyond radio, astronomers have searched for other types of signals. Optical SETI looks for brief, intense, laser pulses that an advanced civilization might use to communicate across interstellar distances. Lasers can be focused into tight beams that don't spread out as much as radio waves, making them potentially more efficient for point-to-point communication between stars. Several observatories have conducted optical SETI surveys, scanning thousands of stars for nanosecond duration laser flashes. So far, nothing definitive has been found. Astronomers have also searched for what are called technosignatures, signs of technology that don't involve deliberate communication. These could include the infrared signatures of Dyson spheres or Dyson swarms, enormous structures built around stars to capture their energy. In 2015, astronomers noticed unusual dimming patterns in a star called KIC 8462852, informally known as Tabby's star, after the astronomer Tabitha Boyajian, who led the study. The star's brightness dipped irregularly by up to 22%, far more than a transiting planet could explain. Some speculated that the dimming might be caused by an alien megastructure, a partially completed Dyson swarm, but subsequent observations strongly suggested the dimming was caused by dust, not technology. The excitement faded. Tabby's star turned out to be a natural phenomenon, not evidence of an advanced civilization. Surveys of hundreds of thousands of galaxies have searched for signs of civilizations that might have harnessed the energy of entire galaxies. If a civilization or group of civilizations built Dyson structures around a significant fraction of the stars in a galaxy, that galaxy would look different in infrared light. It would appear dimmer in visible wavelengths and brighter in infrared, because the structures would absorb starlight and re-radiate it as heat. In 2015, a study examined 100,000 galaxies using data from NASA's Wide Field Infrared Survey Explorer, or WISE, looking for galaxies with unusually high infrared emissions. None showed the expected signature of a galaxy-spanning civilization. 100,000 galaxies examined, and not one showed signs of large-scale energy harvesting. We've also looked for evidence closer to home. If an advanced civilization had visited our solar system at any point in its 4.5 billion year history, they might have left behind artifacts, probes, monitoring stations, beacons, or other technology. We've examined the surfaces of the Moon and Mars in considerable detail using orbiters and rovers. We've sent spacecraft past every planet in our solar system and through the asteroid belt. We've studied thousands of asteroids and comets up close, and we found nothing artificial. No probes hidden in the asteroid belt, no monitoring stations on the far side of the moon, no beacons orbiting any of our planets, just rocks, ice, craters, and silence. The absence of probes is particularly significant because self-replicating probes, often called von Neumann probes, after mathematician John von Neumann, who first described self-replicating machines, could theoretically explore and fill an entire galaxy in a relatively short time. The concept is simple and elegant. You build a probe capable of traveling to another star system. When it arrives, it uses local resources, asteroids, comets, rocky debris, the raw materials that exist in abundance around virtually every star, to build copies of itself. Those copies travel to other star systems, where they build more copies. Each copy builds more copies. The process repeats exponentially. 1 becomes 2, 2 become 4, 4 become 8. Starting from a single probe, you could have billions of probes spread across the galaxy within a few million years. The math of exponential growth is relentless and powerful. Even at speeds much slower than light, even at just a fraction of 1% of light speed, the exponential growth of self-replicating probes means the galaxy could be thoroughly explored in a small fraction of its lifetime. Perhaps 10 million years, perhaps 50 million. It depends on assumptions about speed and replication time. But in every scenario, it's a blink of an eye compared to the galaxy's 13 billion year history. If any civilization anywhere in the Milky Way had ever launched such probes at any point in those 13 billion years, those probes should be everywhere by now, including in our solar system. But we found nothing. Now it's important to be honest about the limitations of our search. Because while we have looked, we haven't looked everywhere. And we haven't looked at everything. Not even close. The Milky Way contains somewhere between 100 billion and 400 billion stars. Even the most ambitious SETI projects have surveyed only a tiny fraction of them. Breakthrough. Listen, the most comprehensive program currently running targets 1 million stars. That's impressive by human standards, a monumental achievement of engineering and dedication, but it's still less than 1,000% of all the stars in the galaxy. It's like searching for a needle in a haystack by examining a few strands of hay. Or perhaps more accurately, it's like searching the entire ocean for a specific fish by scooping up 1 cup of water and checking what's inside. Furthermore, we've only searched a limited range of frequencies. Radio waves span an enormous spectrum, and we don't know what frequency an alien civilization might choose to broadcast on. We tend to focus on frequencies near the hydrogen line or the water hole, a range of frequencies between hydrogen and hydroxyl emission lines that scientists consider logical for interstellar communication. But these choices are based on human logic. An alien civilization might choose completely different frequencies for reasons we can't anticipate. They might communicate using something other than radio waves entirely. Gravitational waves, neutrinos, modulated gamma rays, or technologies we haven't conceived of yet. Our search is necessarily biased toward the kinds of signals we know how to detect with the technology we currently have. There's also a temporal dimension to the problem that's often overlooked. Radio signals travel at the speed of light. A signal broadcast from a star 1,000 light years away would take 1,000 years to reach us. If a civilization broadcast a signal 500 years ago and then stopped, we'd have a window of only about 500 years to detect it, assuming we were within range. If we weren't listening during that window, if we hadn't built radio telescopes yet, Or if our telescopes were pointed in the wrong direction, we'd miss it entirely. Civilizations might rise and fall in time frames shorter than the light travel time between stars. A civilization might flourish for 10,000 years and then go extinct, but if it's 5,000 light years away, its signals are still traveling toward us. And by the time they arrive, the civilization that sent them might have been dead for millennia. We might be searching the right places, but at the wrong times. The universe could be full of signals from civilizations that have already gone silent, signals that have passed through our solar system and continued on into space long before we built the instruments to hear them. And our search has been limited in duration as well. We've been listening for about 65 years. That's nothing on cosmic timescales. The Milky Way is over 13 billion years old. 65 years of searching represents such a vanishingly small fraction of that history that it barely registers. It's like listening for a conversation at a crowded party for 1/10,000,000th of a second, and then concluding that nobody is talking. You wouldn't expect to catch much in that sliver of time. The universe has been here for an incomprehensibly long time. We've been paying attention for an eye blink. Despite all these caveats, despite all the limitations of our search, the silence is still striking. Because there are certain things we should see regardless of whether we're looking in the right place at the right time with the right instrument. Even with our limited search, there are certain things we would expect to see if the galaxy were filled with advanced civilizations, and we don't see them. If even a single civilization had built Dyson structures around a significant fraction of the stars in our region of the galaxy, we would have noticed the altered infrared signatures of those stars. Our infrared telescopes survey the entire sky. We would have seen the waste heat. We haven't. If a civilization had colonized a large portion of the galaxy, transforming worlds and harnessing energy on a massive scale, the effects on stellar populations and galactic chemistry should be detectable with instruments we already have. They're not. If self-replicating probes had filled the galaxy, we should have encountered one by now, or at least found evidence of one in our solar system. We've sent spacecraft throughout the inner solar system, past the outer planets, and into the Kuiper belt. We've mapped the Moon and Mars in extraordinary detail. We haven't found a single artifact that isn't of human origin. The kinds of civilizations that the numbers say should exist, galaxy-spanning civilizations with billions of years of development behind them, would not be subtle. They would not be easy to miss. They would alter their environments on scales that would be visible across interstellar distances, visible to instruments far less sophisticated than what we currently possess. The fact that we see none of this is genuinely puzzling. It's not just that we haven't found what we're looking for, it's that the thing we're looking for, if it existed at the scale the numbers predict, should be impossible to miss. And here's what makes the Fermi Paradox different from other unsolved questions in science. Most scientific mysteries involve things we can see but don't understand. We can see dark matter's gravitational effects but don't know what it is. We can see the universe expanding but don't know why it's accelerating. We can see quantum particles behaving strangely but don't fully understand why. The Fermi Paradox is the opposite. It's about something we don't see that we think we should. It's the absence of evidence that's troubling, not the presence of something unexplained. And in science, absence of evidence is complicated. It can mean the thing you're looking for doesn't exist, or it can mean you're not looking in the right way, in the right place, or at the right time. This distinction matters enormously. The Fermi Paradox is not proof that extraterrestrial civilizations don't exist. It is not evidence that we are alone. It is a problem of expectation versus observation. Our best understanding of the universe leads us to expect abundant life and widespread civilizations. Our observations so far don't confirm that expectation. Something in our reasoning must be wrong, or something about the universe is different from what we assume. Either our estimates about the likelihood of life and intelligence are too optimistic, or civilizations are out there but hidden from us for reasons we don't yet understand. Or there is something about the nature of life, intelligence, or the universe itself that we're missing entirely. The paradox sits at the intersection of astronomy, biology, physics, and philosophy. It touches on questions about the nature of life, the probability of intelligence, the longevity of civilizations, the limits of technology, and the structure of the universe itself. It is, in many ways, the ultimate scientific question. Not just whether we're alone in this vast cosmos, but why the universe looks the way it does when the numbers say it should look different. Enrico Fermi died of stomach cancer in 1954, just 4 years after asking his famous question. He was only 53 years old. He never saw the first SETI search. He never saw the discovery of exoplanets or the mapping of the cosmic microwave background, or the detection of organic molecules in interstellar space. He never lived to see the Kepler telescope reveal that planets are as common as stars. He never saw the evidence pile up, decade after decade, that makes his question even more pointed and more haunting than it was in 1950. But the question endures. It has outlived its author by more than 7 decades and shows no sign of being resolved. If anything, it has become sharper with time. Every new discovery of a habitable zone planet, every new detection of organic molecules in space, every new confirmation that the building blocks of life are universal, all of it makes the silence louder. Where is everybody? We've looked at the sky with some of the most sensitive instruments ever built. We've surveyed thousands of stars. We've scanned millions of frequencies. We've searched for structures, signals, probes, and artifacts. And the answer so far is the same as it was in 1950. Silence. The question now becomes why? Why is the universe so silent? What could possibly explain the gap between the abundance we expect and the emptiness we observe? The possible answers span an extraordinary range, from the deeply mundane to the genuinely terrifying. And each possible answer tells us something different about the nature of life, intelligence, and our own future. Let's walk through the possibilities. And I want to be clear about something from the start. Nobody knows which of these explanations is correct. Some are more popular among scientists than others. Some have more evidence behind them, but none has been proven. The Fermi Paradox remains an open question, one of the great unsolved problems in science. What we can do is lay out the major categories of explanation, examine the logic and evidence behind each one, and try to understand what each would mean for us if it turned out to be true. Because some of these answers are reassuring, and some of them are genuinely terrifying. The first category of explanation is what scientists call the rare Earth hypothesis. The idea, put simply, is that while the universe might be full of planets and perhaps even full of simple microbial life, the conditions required for complex life, and especially intelligent life, are so extraordinarily specific, so dependent on such an unlikely combination of factors that it almost never happens. Earth might not be just one habitable world among billions. It might be a freak accident, a cosmic lottery winner, a planet where an almost impossibly unlikely chain of events produced something that the universe almost never produces. Think about what it actually took for intelligent life to arise on Earth. It wasn't just a matter of having the right temperature and some liquid water. The story of life on this planet is a story of contingencies, of events that didn't have to happen, of lucky breaks that could easily have gone the other way. Start with the planet itself. Earth sits in the habitable zone of a stable, long-lived star. That's necessary but not sufficient, not even close. Earth also has a large moon, one that's unusually large relative to the planet it orbits. Our moon was probably formed about 4.5 billion years ago, when a Mars-sized body slammed into the young Earth at a glancing angle, blasting an enormous amount of debris into orbit that eventually coalesced into the moon. This was a catastrophic, violent, spectacularly unlikely event. The impacting body had to hit at just the right angle and just the right speed. A slightly different collision could have shattered both worlds or sent the debris flying off into space instead of into orbit. And yet the moon that this unlikely collision created plays a crucial role in making Earth habitable for complex life. The moon stabilizes Earth's axial tilt, preventing the kind of extreme wobbling that would cause wild climate swings over millions of years. Without the moon, Earth's axis could tip chaotically, swinging from nearly upright to nearly sideways. Seasons would become extreme and unpredictable. Polar regions might face the sun directly for centuries, then plunge into darkness. The climate chaos would make it extraordinarily difficult for complex ecosystems to develop and persist over the billions of years needed for intelligence to evolve. Earth also has a strong magnetic field, generated by the churning of molten iron in its core. This magnetic field acts as an invisible shield, deflecting the charged particles of the solar wind and protecting the atmosphere from being slowly stripped away into space. We can see what happens without this shield by looking at Mars. Mars once had a magnetic field, but its smaller core cooled and solidified, shutting the field down. Without that protection, the solar wind spent hundreds of millions of years slowly eroding the Martian atmosphere, molecule by molecule, carrying it off into space. Mars went from a world that likely had liquid water on its surface, maybe even rivers and lakes, to the cold, barren desert we see today. Its atmosphere is now less than 1% as thick as Earth's. Earth kept its magnetic field because it's larger than Mars, so its core stayed hot and liquid longer. But that's not guaranteed for every rocky planet. It depends on the planet's size, its composition, how much radioactive material it contains to generate internal heat. A planet could sit perfectly in a habitable zone, have liquid water, have all the right chemistry, and still lose its atmosphere because it lacked a magnetic field. And without an atmosphere, liquid water can't persist on the surface. It either freezes or boils away into the vacuum of space. Then there's plate tectonics. Earth is the only planet in our solar system with active plate tectonics. The slow but relentless movement of continental plates across the surface. This might seem like a geological curiosity irrelevant to the question of life, but plate tectonics plays a vital and perhaps essential role in regulating Earth's climate over billions of years. The movement of plates drives a carbon cycle that acts as a planetary thermostat. Carbon dioxide, a greenhouse gas, is pulled from the atmosphere by weathering of rocks and dissolved into the oceans. It's then carried into the Earth's interior through subduction. where one tectonic plate slides beneath another. Eventually, that carbon is released back into the atmosphere through volcanic eruptions. This cycle keeps atmospheric carbon dioxide within a range that maintains temperatures suitable for liquid water over immense timescales. Without plate tectonics, this thermostat breaks down. A planet might gradually accumulate too much carbon dioxide and overheat, like Venus did, or lose too much and freeze. Whether plate tectonics is common on rocky planets throughout the galaxy, or a rare feature specific to certain planetary compositions and sizes, remains one of the open questions in planetary science. Jupiter, the massive gas giant in our outer solar system, may also have played a critical and perhaps underappreciated role in Earth's story. Jupiter's enormous gravity acts like a cosmic shield, deflecting or capturing many comets and asteroids that might otherwise have impacted Earth. The inner solar system is a shooting gallery. Rocks and ice hurtle through it constantly, remnants of the solar system's formation. Without Jupiter sweeping up much of this debris or flinging it out of the solar system entirely, the rate of devastating impacts on Earth might have been much higher, potentially sterilizing the planet's surface repeatedly and preventing complex life from ever getting established. Some scientists have argued that having a large gas giant in the right orbit at the right distance is an important and perhaps uncommon ingredient for a truly habitable planetary system. So the rare Earth hypothesis stacks up these requirements. A star of the right type, a planet in the habitable zone, a large stabilizing moon formed by an unlikely collision, a magnetic field strong enough to protect the atmosphere, active plate tectonics to regulate the climate, a gas giant to shield against asteroid impacts. Each requirement, taken individually, might not be that rare, but when you multiply them all together, the probability of getting all of them on a single planet drops sharply. And we haven't even gotten to the biological requirements yet. Even if you have a perfectly set up planet, life still has to actually arise. And we genuinely don't know how difficult that step is. On Earth, life appeared relatively quickly, within a few 100 million years of conditions becoming suitable. Some scientists take this as evidence that the origin of life is easy, that given the right conditions, it happens almost inevitably. But others point out that we have a sample size of exactly one. We can't draw reliable statistical conclusions from a single example. Earth might have just gotten fantastically lucky. The origin of life might be an extraordinarily improbable event that happened to occur here by chance, and might not have happened on any of the other 40 billion potentially habitable planets in our galaxy. Without finding life elsewhere, we simply cannot know which interpretation is correct. But here's where the argument becomes most compelling. Even if simple life is common, the jump to complex life might be extraordinarily rare. On Earth, simple single-celled organisms existed for roughly 3 billion years before complex multicellular life appeared. 3 billion years. That's an almost incomprehensible stretch of time. For 3/4 of the entire history of life on this planet, nothing existed but microbes. No animals, no plants, no eyes, no brains, no movement beyond the drifting of single cells. Just bacteria and archaea floating in the ocean, forming mats on rocks, cycling chemicals in the dark. The world was alive, but it was a profoundly simple kind of alive. Nothing you would recognize as a living thing if you saw it. The breakthrough that eventually led to complex life was a specific event that scientists believe happened only once in Earth's entire history. Around 2 billion years ago, one simple cell, an archaeon, engulfed another cell, a bacterium, and instead of digesting it, the two cells entered into a permanent partnership. The engulfed bacterium became the mitochondrion, the energy-producing structure found inside virtually all complex cells today. Mitochondria are what give complex cells their power. They're the reason animal cells can produce enough energy to build large, active, multicellular bodies. Without mitochondria, cells are limited to relatively simple metabolisms. They can survive, but they can't do much. The energy supplied by mitochondria is what made it possible for cells to grow larger, to specialize, to cooperate in the vast multicellular structures that became animals and plants and fungi. This event, called endosymbiosis, is the foundation of all complex life on Earth. Every animal, every plant, every fungus, every complex organism that has ever lived is descended from that single ancient partnership. And the evidence strongly suggests it happened only once. In 4 billion years of life on Earth, across countless trillions of cellular interactions, this particular merger occurred exactly one time. That's a staggering fact. If this event were easy, if it were a natural and likely outcome of cellular evolution, you would expect it to have happened many times independently. The fact that it appears to have happened once suggests it might be phenomenally unlikely. And if that's the case, the universe could be full of planets, teeming with simple microbial life, oceans filled with bacteria, but almost completely devoid of anything more complex. A cosmos crawling with microbes, but empty of minds. And intelligence itself might be yet another improbable step. Life on Earth has existed for roughly 3.5 billion years. In that time, evolution has produced an extraordinary diversity of organisms. Millions of species exist today. Billions of species have existed over Earth's history. And out of all those billions of species, across all those billions of years, only one has developed the kind of intelligence that builds technology and contemplates the universe. Just one. Dolphins are smart. Octopuses are remarkably clever. Crows and ravens use tools and solve complex problems. Elephants have sophisticated social structures and appear to mourn their dead. But none of them build radio telescopes. None of them write equations or launch spacecraft or wonder about the stars. Human-level intelligence, the specific kind of intelligence that leads to science and technology and civilization, evolved exactly once on this planet. If intelligence of this kind were a common outcome of evolution, a natural endpoint that life tends to converge toward, you would expect it to have evolved multiple times independently. Eyes evolved independently at least 40 times in different evolutionary lineages. Wings evolved independently in insects, birds, bats, and pterosaurs. Flight evolved multiple times. But technological intelligence evolved once. That strongly suggests it's not inevitable. It might be a fluke, a quirk of one particular evolutionary lineage on one particular planet, not a general trend that life follows. This chain of reasoning leads to one of the most important and most unsettling concepts in thinking about the Fermi Paradox. The Great Filter. The Great Filter is the idea that somewhere in the long sequence of steps between dead chemistry and a galaxy-spanning civilization, there is at least one step that is almost impossibly difficult to pass. A bottleneck so severe that virtually nothing gets through it. Think of it as a wall that stretches across the path from simple matter to starfaring intelligence. A wall so high that almost nothing climbs over it. The critical question is where in the sequence that wall stands. And the answer to that question has very different implications for humanity depending on which side of the wall we're on. If the Great Filter is behind us, that's the hopeful scenario. It means the hard part is already done. Maybe the origin of life is the filter, so improbable that it almost never happens anywhere. Or maybe the filter is the jump from simple cells to complex cells, the endosymbiosis event that happened only once, or the evolution of intelligence, or the development of technology. If any of these steps is the Great Filter, then we've already passed through the bottleneck. We're on the other side. We're the rare success story, the one civilization in billions that made it through. The silence of the universe is explained not by some terrible fate that awaits us, but by the extraordinary improbability of what we've already achieved. In this scenario, the universe isn't dangerous. It's just empty. And we're not doomed. We're special. But if the Great Filter is ahead of us, that changes everything. That's a terrifying scenario. It means civilizations arise regularly, develop technology regularly, reach roughly our level of advancement regularly, and then something stops them. Something destroys them or silences them before they can spread beyond their home planet. If this is the case, then we're not special at all. We're just the latest in a long line of civilizations marching toward the same cliff edge. And whatever destroyed or silenced all the others is waiting for us too. Somewhere in our future. Something we haven't encountered yet but will. What might such a future filter look like? The most straightforward possibility is self-destruction. A civilization that develops advanced technology simultaneously develops the power to annihilate itself. Nuclear weapons are the most obvious example. For the first time in history, humanity possesses the capability to effectively end civilization within hours. A full-scale nuclear exchange between major powers could directly kill hundreds of millions and trigger a nuclear winter that would collapse global agriculture, potentially killing billions more through starvation over the following years. We've possessed this capability since the 1950s. We've come perilously close to using it on multiple occasions. The Cuban Missile Crisis of 1962. The 1983 Soviet satellite false alarm, when a Soviet officer named Stanislav Petrov chose not to report what his computer screen showed as 5 incoming American nuclear missiles, correctly judging it to be a system malfunction. Had he followed protocol and reported the alert, the Soviet leadership might have launched a retaliatory strike within minutes, starting a nuclear war based on a computer error. The 1995 Norwegian rocket incident, when Russia briefly mistook a scientific research rocket launched from Norway for a potential nuclear strike, and reportedly activated its nuclear briefcase for the first time ever documented. President Boris Yeltsin had just minutes to decide whether to launch a counterattack before the mistake was recognized. Each of these events could have ended differently. Each could have triggered a war that killed billions. We survived through a combination of good judgment and luck. But luck runs out. And nuclear weapons might not even be the most dangerous technology we face. Climate change, driven by the burning of fossil fuels, is altering Earth's atmosphere and ecosystems in ways that could destabilize civilization over the coming century. Engineered biological weapons could create pandemics far worse than anything nature has produced. Artificial intelligence, if developed without sufficient care and safeguards, could pose existential risks that we're only beginning to comprehend. Each of these threats emerges naturally from the same intelligence and curiosity that makes civilization possible in the first place. The drive to discover, to innovate, to harness energy and master the natural world. This drive is what builds civilizations, but it also inevitably produces the very tools that can destroy them. If this pattern is universal, if every intelligent species that develops technology inevitably develops these same dangerous capabilities as a natural byproduct of the same curiosity that makes them intelligent in the first place, then every technological civilization in the galaxy faces the same gauntlet. And if even a modest fraction of them fail to survive it, the silence is explained. But self-destruction isn't the only possible future filter. There are other scenarios that will produce the same cosmic silence without requiring extinction. One fascinating possibility is that civilizations don't destroy themselves, but instead turn inward. Perhaps the natural trajectory of an advanced civilization is not outward expansion across the stars, but retreat into virtual realities so rich and immersive that the physical universe becomes irrelevant. Why spend millions of years and unimaginable resources crossing the hostile void between stars when you can create entire simulated universes inside computers on your home world? Universes where the laws of physics can be whatever you want, where suffering is optional, where every desire can be fulfilled. If virtual worlds become sufficiently compelling, and if the cost of interstellar travel remains sufficiently high, then perhaps every civilization eventually makes the same rational choice. They stay home. They turn their gaze inward rather than outward. They build paradise inside a machine and never bother to colonize the galaxy. From the outside, such civilizations would be invisible. They'd still exist, but they produce no signals, no megastructures, no probes, no evidence that we could detect. Another possibility involves the way civilizations communicate. Our entire search for extraterrestrial intelligence is built on assumptions about how alien civilizations would behave. Assumptions based on our own technology and our own way of thinking. We search primarily for radio waves because that's what we know how to detect, but a civilization even a few hundred years more advanced than us might communicate using methods we haven't invented yet and can't even imagine. They might encode information in gravitational waves, or in modulated neutrino beams, or in quantum entangled particles, or in some physical phenomenon that human science hasn't yet discovered. Searching for their signals with radio telescopes might be like trying to detect the internet using a pair of binoculars. The medium is simply invisible to the instrument you're using. If every advanced civilization rapidly moves beyond electromagnetic communication to some more sophisticated method, then the galaxy could be buzzing with conversation that we're completely deaf to. Then there's the brute physical reality of cosmic distances. Even if civilizations are common, the spaces between stars are so incomprehensibly vast that contact might be effectively impossible regardless of how advanced a civilization becomes. The speed of light is not just very fast, it's the absolute speed limit of the universe, a fundamental law of physics that cannot be broken by any technology, no matter how advanced. A signal sent from a civilization 1,000 light years away takes 1,000 years to reach us. If we respond, our reply takes another 1,000 years to arrive. That's a 2,000-year round trip for a single exchange. The civilization that sent the original message might not exist anymore by the time our reply arrives. Their world might have changed beyond recognition. Their language might have evolved into something unrecognizable. They might have gone extinct, or evolved into something entirely different, or simply lost interest in the conversation thousands of years ago. This isn't just an inconvenience. It fundamentally changes the nature of what communication means. At these timescales, dialogue is impossible. What you have instead is something more like sending messages in bottles across an ocean so vast that the bottles take centuries to wash ashore. You're not having a conversation. You're leaving notes for strangers who might or might not exist by the time your note arrives. The universe might be full of such notes, drifting through space at the speed of light, crossing paths, passing through star systems, carrying messages from civilizations that have long since fallen silent. And we might simply be too new to the game to have received any of them yet, or too primitive to recognize them when they pass through our tiny corner of space. There's also the unsettling possibility that advanced civilizations have very good reasons to stay silent. Perhaps the galaxy is not a friendly neighborhood. Perhaps civilizations that broadcast their existence are doing something incredibly dangerous, announcing their location to potential threats they can't see and can't anticipate. This idea, sometimes called the Dark Forest hypothesis, named after the science fiction novel by Chinese author Liu Cixin, suggests that the safest strategy for any civilization in a universe where you can't know the intentions of others is to remain hidden. If you detect another civilization, you face a dilemma. Are they friendly? Are they a threat? You can't know, and by the time you find out, it might be too late. The rational response under these assumptions is to stay quiet and hope no one notices you. If most civilizations reach this conclusion independently, the galaxy would be full of hidden civilizations, all deliberately avoiding detection, all watching the sky in silence, all afraid to speak first. The silence wouldn't mean the galaxy is empty. It would mean the galaxy is afraid. This is a chilling idea, but it's worth noting that it rests on specific assumptions about the nature of alien civilizations that might not be correct. It assumes that civilizations are inherently competitive and potentially hostile. It assumes that the risks of contact outweigh the benefits. These assumptions might apply to some civilizations, but not others. A single civilization that chose to break the silence would undermine the entire premise. Finally, there's a possibility that doesn't require any exotic explanation at all. Perhaps we're simply too early. The universe is 13.8 billion years old, but most of the stars that will ever exist haven't been born yet. The universe has a long, long future ahead of it. Red dwarf stars, which make up the vast majority of stars in the galaxy, can burn steadily for trillions of years, far longer than the current age of the universe. The era of star formation is not winding down. It still has an immense span ahead of it. We might be among the first technological civilizations to arise, not because life is rare, but because the universe is still young. Most civilizations might emerge billions of years from now, around long-lived red dwarf stars, in a universe that has calmed down from the violent supernova explosions and gamma-ray bursts that characterized its turbulent youth. In this view, the silence isn't permanent. It's temporary. We're just early to the party, and the guests haven't arrived yet. Each of these explanations, the rare Earth hypothesis, the great filter behind us, the great filter ahead of us, the retreat into virtual worlds, the use of undetectable communication methods, the isolation imposed by cosmic distances, the dark forest silence, and the possibility that we're simply early. Each of these fits the observed evidence. Every single one of them is consistent with a universe that appears silent and empty from our perspective. That's what makes the Fermi Paradox so maddening. It's not that we have no explanations, we have too many, and we don't yet have enough information to tell which one is right. No scientist can honestly look at this problem and tell you they know the answer. Anyone who claims certainty is selling you something. The honest position is uncertainty. Deep, uncomfortable, profound uncertainty. We don't know why the universe is silent. We don't know if we're alone. We don't know if the filter is behind us or ahead of us. We don't know if the galaxy is truly empty or full of hidden civilizations watching us from the dark. What we do know is that each possible answer carries enormously different implications for humanity. If the filter is behind us, we're precious. Perhaps the only technological civilization in the galaxy, carrying a weight of cosmic significance we can barely comprehend. If the filter is ahead of us, we're in danger. And the decisions we make in the coming centuries might determine whether we become the exception that survives, or another silent ruin on a forgotten world. If space is simply too vast, we're isolated. And we may need to come to terms with the possibility that we'll never know if we have neighbors. And if we're simply too early, then the silence is temporary, and the universe's story is only just beginning. But regardless of which answer turns out to be true, the paradox itself teaches us something valuable. It forces us to confront the true scale of our ignorance about the universe and our place in it. It reminds us that the deepest questions in science are often not about what we know, but about what we don't know and what that ignorance might mean. And it raises a question that goes beyond science entirely. A question about what this profound silence means for how we live, what we value, and what we owe to the future. Something remarkable has happened since Fermi asked his question over 7 decades ago. The paradox hasn't weakened with time, it has intensified. Every major astronomical discovery of the past half-century has added weight to one side of the equation without adding anything to the other. We keep finding reasons the universe should be full of life, and we keep finding no life. The scale tips further and further with each passing year, and the silence grows louder. When Fermi sat down to lunch in 1950, we didn't know if other stars had planets. Now we know virtually all of them do. We didn't know the chemistry of life was common beyond Earth. Now we find amino acids on meteorites and organic molecules drifting between the stars. We didn't know how quickly life could arise from raw chemistry. Now the geological record on Earth tells us it happened almost as soon as conditions permitted. Each of these discoveries was celebrated, and rightly so. Each one expanded our understanding of the cosmos. But each one also deepened the paradox. Each one made the silence harder to explain. Each one made Fermi's question sharper and more urgent. And the discoveries haven't stopped. Right now, in this moment, we are living through what might be the most important era in the history of the search for life beyond Earth. The James Webb Space Telescope, launched in 2021, is the most powerful space observatory ever built. Among its many capabilities, it can analyze the atmospheres of exoplanets by studying the light that passes through them as they transit their host stars. Different molecules absorb different wavelengths of light. By examining which wavelengths are missing, astronomers can determine what gases are present in a distant planet's atmosphere. If an exoplanet's atmosphere contains oxygen alongside methane, that would be a powerful indication of biological activity, because those two gases react with each other and would quickly disappear from an atmosphere unless something, presumably life, was constantly replenishing them. Webb has already begun studying the atmospheres of rocky planets in the TRAPPIST-1 system. Within the next decade or two, as Webb studies rocky worlds around small stars and future observatories are designed specifically to image Earth-like planets around Sun-like stars, we may begin to build the first catalogue of living worlds beyond our solar system. If that analysis reveals biosignatures, gases that are best explained by the presence of life, it would transform the Fermi Paradox overnight. It would tell us that life is not unique to Earth, that the chemistry of biology is a repeatable phenomenon, not a one-time accident. Closer to home, NASA's Europa Clipper mission, launched in 2024, will arrive at Jupiter's moon Europa around 2030. Europa almost certainly harbours a global ocean of liquid water beneath its icy crust, an ocean that might contain twice as much water as all of Earth's oceans combined. The Clipper will fly past Europa dozens of times, sampling any material that may be venting from beneath the ice through cracks in the surface. Observations from the Hubble Space Telescope have hinted at possible water vapor plumes erupting from Europa, though these detections remain unconfirmed. If plumes do exist, the Clipper could fly directly through them, capturing samples of the ocean below without ever having to drill through the ice. It will search for the organic molecules and chemical energy sources that life requires. It won't be able to detect life directly, but it can determine whether the conditions for life exist beneath Europa's ice. And on Mars, the Perseverance rover has been collecting and caching rock samples on the Martian surface, samples intended to be returned to Earth by a future Mars sample return mission that is still being redesigned after its original plan was deemed too costly. Those samples, sealed in tubes and left on the Martian surface, may contain fossilized evidence of ancient microbial life from a time when Mars had liquid water on its surface. Between web-scanning exoplanet atmospheres, Europa Clipper probing a subsurface ocean, and Perseverance caching Martian rocks for eventual return, we are assembling the tools to test the question of cosmic life directly for the first time. We stand at a threshold. Within the next 10 to 20 years, we will have data that Fermi never had, that no generation before us has had. Data that could begin to resolve the paradox one way or another. We might discover that life is common, which would deepen the mystery of why the universe is silent. Or we might discover that every world we examine is sterile, which would suggest we are rarer than we imagined. Either result would reshape our understanding of our place in the cosmos. Either result would matter enormously. But regardless of what those missions find, the question the paradox raises goes beyond science. It goes beyond data and telescopes and atmospheric spectra. Because the Fermi Paradox is not just a question about what's out there. It's a question about what it means that we're here. So, what does this all mean for us? What does it mean for humanity, for how we think about ourselves, for how we treat our planet, for how we plan our future? Let's start with the most hopeful interpretation. If the Great Filter is behind us, if the silence exists because the steps leading to intelligent life are extraordinarily rare and we've already passed through them, then we are almost inconceivably precious. Think about what that would mean. Out of all the trillions of planets in the observable universe, across all the billions of years that the cosmos has existed, we might be one of the only civilizations, perhaps the only civilization, that has ever looked up at the stars and wondered what they are. The atoms that make up your body were forged in the cores of stars that exploded billions of years ago. Those atoms drifted through space for eons, eventually coming together on this one small planet, assembling themselves through billions of years of evolution into a being that can think, that can feel, that can answer questions about its own existence. If that process is truly rare, if it almost never happens anywhere, then you are not just a person living an ordinary life. You are one of the rarest and most remarkable things in the entire universe. A piece of matter that became aware of itself. A fragment of the cosmos that learned to contemplate the cosmos. In this scenario, every human life takes on a weight that's difficult to articulate. Every mind that thinks, every heart that feels, every hand that creates, all of it is precious beyond measure. Not because some external authority declares it so, but because it might be among the only instances of consciousness that the universe has ever produced in this entire region of space. The laughter of a child, the brush strokes of a painter, the equations of a physicist, the compassion of a stranger, all of this might be happening only here. Nowhere else for hundreds or thousands of light years in every direction. Maybe nowhere else in the entire galaxy. The silence of the universe in this interpretation is not something to mourn. It's something that makes what's happening on this planet all the more extraordinary. But this interpretation also carries a responsibility that's staggering in its weight. If we are rare, if intelligent life is a cosmic anomaly, then what happens on Earth doesn't just matter for us. It might matter for the universe itself. We might be the only way this corner of the cosmos has of knowing itself, of understanding itself, of appreciating its own beauty and complexity. If we destroy ourselves, if we render our planet uninhabitable, we wouldn't just be ending human civilization. We might be extinguishing the only light of consciousness for a billion light years in every direction. The universe would continue existing, of course. Stars would burn, planets would orbit, galaxies would spiral, but there might be no one left to witness it, to understand it, to find meaning in it. The cosmos would become a vast and magnificent machine with no one to appreciate what it is. Now let's consider the darker interpretation. If the great filter is ahead of us, if the silence exists because civilizations regularly reach our level of advancement and then fail, then we're in danger, serious danger. Because whatever destroyed all those other civilizations is still out there, waiting in our future. And we don't know what it is. Maybe it's nuclear war. Maybe it's climate collapse. Maybe it's a pandemic, natural or engineered. Maybe it's artificial intelligence that doesn't share our values. Maybe it's something we haven't thought of yet. Some technology or challenge that we'll encounter in the next century or the next millennium that will test us as nothing has tested us before. In this scenario, the Fermi Paradox becomes a warning. The silence of the sky is not just a scientific puzzle. It's a message written in the absence of others. It says that getting to where we are is not the hard part. The hard part is what comes next. Every civilization faces it. Almost none survive it. And we're approaching it now at this precise moment in our history with nuclear arsenals that could end civilization in an afternoon. With a climate that's changing faster than our institutions are adapting, with biological tools that could create pathogens of unprecedented lethality, with artificial intelligence that's advancing faster than our ability to understand its implications, and with geopolitical tensions that make cooperation on these challenges harder than it should be. The filter, if it lies ahead, might not be a single catastrophic event. It might be a narrow window, perhaps only a few centuries wide, during which a civilization has the power to destroy itself but hasn't yet developed the wisdom, the institutions, or the collective restraint to refrain. If the window is narrow enough, and if most civilizations fail to navigate it, the galaxy fills with silence, world after world reaching the brink, civilization after civilization stepping over the edge. This interpretation should sober us, not paralyze us with fear, but make us take seriously the choices we're making right now, in this century, on this planet. Because if the filter is ahead, the decisions we make about nuclear weapons, about climate change, about biotechnology, about artificial intelligence, these aren't just policy questions, they're existential ones. They might determine whether humanity joins the ranks of the civilizations that survived, or the civilizations that didn't. Whether our descendants look back at this era as the time we almost lost everything, or the time we turned the corner and ensured our long-term survival. There's a strange and uncomfortable symmetry between these two interpretations. If the filter is behind us, we're precious and we need to protect what we have because it's irreplaceable. If the filter is ahead of us, we're in danger and we need to protect what we have because we might lose it. Either way, the conclusion is the same. What happens on Earth matters enormously. Whether we're rare or whether we're fragile or both, the imperative is identical. Take care of this planet. Take care of each other. Build wisely. Think long-term. Don't squander what might be the only shot at consciousness that this region of the universe will ever get. The Fermi Paradox also changes how we think about the search for life beyond Earth. Every new discovery in astrobiology, every probe we send to another world, every telescope we point at an exoplanet's atmosphere is not just an exercise in scientific curiosity. It's a data point in the most important question we've ever asked. Are we alone? We talked about those, upcoming missions and what they might find. But let's think carefully about what their results would actually mean for the paradox. If any of those missions discovers simple microbial life, it would be one of the greatest scientific discoveries in human history. It would mean that life is not unique to Earth, that the chemistry of biology is not a one-time accident, but a repeatable phenomenon. Headlines around the world would celebrate it, and rightly so. But it would also have a troubling implication for the Fermi Paradox. If simple life arose independently on two worlds in the same solar system, it would strongly suggest that the origin of life is easy, that it happens readily whenever conditions allow. And if the origin of life is easy, then it's probably not the great filter. The filter must be somewhere else, somewhere further along the chain from microbes to starfaring civilizations. That would push the filter closer to us in the sequence, making it more likely that the filter lies ahead of us, not behind us. Finding life on Mars or Europa would be thrilling scientifically, but unsettling existentially. It would mean that whatever is preventing civilizations from filling the galaxy, it isn't the rarity of life itself. It's something else. Something that happens later. Something that might happen to us. Conversely, if we search the solar system thoroughly and find no life anywhere except Earth, that would be strangely reassuring. It would suggest that the origin of life is the hard step, the great filter, and that we've already passed through it. Finding a sterile Mars, a lifeless Europa, a dead and barren Enceladus, these would be deeply disappointing discoveries in one sense, but quietly hopeful in another. They would suggest that we're rare, not doomed. This is one of the strangest aspects of the Fermi Paradox. It reverses our intuitions about what counts as good news and bad news. Normally, finding life elsewhere would be celebrated as wonderful news, And it would be, scientifically. But in the context of the Fermi Paradox, it carries a shadow, and normally finding that other worlds are sterile would be seen as disappointing. But in this context, it carries a note of hope. Beyond its scientific implications, the Fermi Paradox confronts us with something deeply philosophical, something that touches on what it means to be human. It forces us to sit with the possibility that we might be alone. Not alone in the sense of being lonely at a party, but alone in the deepest and most absolute possible sense. Alone in the universe. The only minds, the only consciousness, the only beings in the entire observable cosmos who can wonder, who can love, who can grieve, who can create art and music and poetry, who can look up at the stars and ask why they're there and what they mean. For most of human history, we assumed we were at the center of creation, the most important beings in a cosmos designed for us. Science gradually dismantled that assumption. Copernicus showed we weren't at the center of the solar system. Galileo showed we were just one planet among several. Darwin showed we were one species among millions, shaped by the same evolutionary forces as every other creature. Hubble showed our galaxy was one among billions. Modern cosmology showed the universe had no center at all. Each discovery made us smaller, less central, less special. The Fermi Paradox potentially reverses this long trend of cosmic demotion. If we're truly alone, or effectively alone because no other civilization has survived or made itself known, then we might be more special than we ever imagined. Not special because we're at the center of anything, but special because we exist at all. Because in a universe that appears capable of producing life, something has prevented life from filling it, and we're among the vanishingly few, perhaps the only ones, who made it through. That's a different kind of special. It's not the comfortable specialness of being chosen or central, it's the uncomfortable specialness of being improbable, of existing against enormous odds, of being a flicker of awareness in a vast, mostly unconscious cosmos. And this brings us to perhaps the most profound lesson of the Fermi Paradox. It's a mirror. When we look at the silence of the universe and ask why, the answers we lean toward reveal something about ourselves, about our hopes and our fears, and our assumptions about the nature of intelligence. If we lean toward the rare Earth hypothesis, we might be expressing a deep human need to feel special, to believe that we matter, to find significance in a cosmos that seems indifferent. If we lean towards the self-destruction filter, we might be projecting our own anxieties about nuclear war and climate change and political instability onto the cosmos, reading our own fears into the darkness between the stars. If we lean toward the dark forest hypothesis, we might be revealing our own fears about the intentions of strangers, the same fears that shape so much of human history and human conflict. If we lean toward the idea that civilizations retreat into virtual worlds, we might be reflecting our own growing relationship with technology and screens and digital realities, the way so many of us already spend more time in virtual spaces than in the natural world. The Fermi Paradox doesn't just ask a question about the universe, it asks a question about us. What do we believe about the nature of intelligence? What do we fear about the trajectory of civilization? What do we hope for when we look at the stars? The paradox also reminds us that science is, at its heart, a process, not a collection of settled answers. The greatest questions in science are the ones that remain open, the ones where honest uncertainty is the only appropriate response. The Fermi Paradox is one of those questions. It might be resolved in our lifetimes. A radio signal from another civilization, a biosignature in an exoplanet's atmosphere, even a confirmed sterile Mars. Any of these could shift the balance of evidence dramatically. Or it might remain open for centuries, a question that each generation inherits from the last, each adding new data but never quite reaching a definitive answer. And that's fine. Not every question needs to be answered to be valuable. Sometimes the question itself is the point. The Fermi Paradox has inspired decades of scientific research. It has driven the search for exoplanets, the development of new telescopes, the exploration of Mars, the study of extremophiles on Earth, and the development of the field of astrobiology. It has pushed us to think more carefully about the conditions for life, the probability of intelligence, and the long-term survival of civilizations. Even without an answer, the question has made us wiser. So where does this leave us? We've traveled a long way tonight. We start with the staggering numbers: 200 billion trillion stars, tens of billions of potentially habitable planets in our galaxy alone. The building blocks of life scattered everywhere. Time enough for civilizations to have risen and spread across entire galaxies many times over. We confronted the silence, the complete and total absence of any evidence that anyone else is out there. Despite 65 years of searching, we explored the possible explanations, from the rarity of complex life to the fragility of civilizations, to the vastness of space, to the possibility that we're simply too early or too limited in our search. And we wrestled with what the silence means for science, for our understanding of ourselves, and for the choices we face as a species. The Fermi Paradox doesn't offer us a comfortable conclusion. It doesn't wrap up neatly. There's no satisfying answer at the end that resolves the tension. The tension remains. The universe appears to be a place where life should be abundant, and yet it appears empty. That contradiction sits unresolved, an open wound in our understanding of the cosmos. But perhaps the most important thing the paradox teaches us isn't about the universe at all. It's about us. It's about the fact that we're here. That against whatever odds, through whatever filters, past whatever bottlenecks, we made it. We exist. We're conscious. We can look up at the night sky and understand what we're seeing. Billions of stars, trillions of worlds, distances measured in light years, a universe 14 billion years old, and 93 billion light years across. We can hold all of that in our minds and ask what it means. Whether we're alone or not, whether the silence is permanent or temporary, whether the filter is behind us or ahead, this much is certain. Right now, right here, on this small planet orbiting an ordinary star in one spiral arm of one galaxy among trillions, something remarkable is happening. Matter has organized itself into beings that can wonder about their own existence. The raw material of dead stars has organized itself into minds that can contemplate the cosmos that created them. The universe has produced, at least once, something that can look back at the universe and try to understand it. That's not nothing. That's extraordinary. In a cosmos that might be entirely empty of other minds, it might be the most extraordinary thing that has ever happened. So the next time you step outside on a clear night and look up at the stars, consider what the silence means. Those thousands of points of light scattered across the darkness. Each one is a sun. Many of them have planets. Some of those planets might have liquid water and the right chemistry for life. And yet, as far as we can tell, none of them has produced anyone who has noticed us. contacted us, or left any trace of their existence that we've been able to detect. The sky is full of stars and empty of voices. That fact is either the loneliest thing in the universe or the most precious. It means either that we are cosmically alone, surrounded by silence that will never be broken, or that the universe is filled with others we simply haven't found yet. Either way, what we do here on Earth matters. If we're alone, we carry the only flame of consciousness in a vast, dark cosmos, and letting that flame go out would be a loss beyond calculation. If we're not alone, we still carry a flame, one among many perhaps, but ours unique in its particulars, shaped by the specific history of one planet and one species, and 4 billion years of evolution that unfolded in a way that happened nowhere else. The Fermi Paradox asks where everybody is, but perhaps the more important question is what we do with the fact that we're here. We didn't choose to exist. We didn't choose to be the species that asks these questions, but here we are, and the questions demand something of us. They demand that we take our existence seriously and treat it as something worth defending. That we treat this planet, this biosphere, this fragile and improbable experiment in consciousness with the care it deserves. That we think not just about the next quarter or the next election, but about the next century and the next millennium. That we act as though what happens here matters, because it might matter more than we can possibly imagine. The universe is vast, the silence is deep, the paradox is unsolved, but you are here, on this pale blue dot, under these ancient stars, able to think about all of it, able to wonder, able to feel the weight of the question and the beauty of the mystery. That's remarkable. That's rare. That might be the rarest thing in the entire universe. And perhaps that's the answer the Fermi Paradox has been trying to give us all along. Not an answer about where everybody else is, but an answer about what we are. We are the universe's way of asking the question. And the fact that the question exists at all, the fact that atoms and starlight arrange themselves into a being that can lie awake at night wondering if it's alone, that is itself a kind of answer. Not a complete one, not a comfortable one, but a profound one. The stars are silent, but we are not. And as long as we're here, as long as we keep asking, as long as we keep searching, the question stays alive. The universe made us. We ask the universe why. And for now, that conversation, one-sided as it may be, is the most extraordinary thing happening in the cosmos. Thank you for joining me on this journey tonight. If this exploration meant something to you, a like or subscribe would help me keep making these deep dives into the questions that matter most. And remember, the next time you look up at the night sky, you're not just seeing stars, you're looking at the silence. A silence that might be the emptiness of a universe where life is rare, or the quiet of a universe where life is hidden, or the patience of a universe that's waiting for us to listen better. We don't know which, but the fact that you can stand there under those ancient lights and wonder about it at all, that's something worth celebrating. That's something worth protecting. That might be the most important thing in the universe. Good night, and may the silence of the stars remind you, every time you look up, how extraordinary it is to be alive, to be aware and to be capable of wondering why the universe made you at all.